Hi everybody, Cal here. In this video we're going to cover sections 1.5 solution sets of linear systems and 1.7 linear independence. Again, we're still in the part of the course where everything we're doing is absolutely essential and fundamental to everything else that's going to come after. 1.5 talks about a classification of linear systems based on what's on the right hand side. And then gets into a numerical skill that we'll need. So the first thing it introduces is the idea of a homogeneous linear system. And a system is homogeneous if its right-hand side is zeros. So, we have all the coefficients times the x1s and the x2s and the x3s. Those can be whatever they want, but then the right-hand side equals thing. The thing must be 0. Okay? That's the definition. The right-hand side, the b, is 0. If you're talking about the format ax equals b, b is 0. It says here at the bottom of the page, 43, that any homogeneous solution must be consistent. It always has at least one solution, x equals 0. You should figure out why that is. It's called the trivial solution. Okay, x being 0 is called the trivial solution, and if there is another solution, that solution will be called a non-trivial solution. Make sure you understand the difference. The blurb here, the colored box at the top of 44, is true, but is not a definition. Be aware. Example 1 illustrates why this thing should be true. So do work through that. And example 2 is another good, sorry, my cat is being loud. Example 2 is another good thing to work through. Then we introduce something called parametric vector form. Whenever we solve a system of equations, we are going to put the solution in what's called parametric vector form. So it is illustrated actually here at the top of the page in example 2. 1 and 2, actually. Okay? We are always going to put our solutions in this format. X is equal to something times one vector plus something times another vector, and so on. And we'll have one something for each free variable. Make sure that you understand how they're doing this in examples 1 and 2, because you will need to do the same thing. Then we get into solutions of non-homogeneous systems. I suggest that you work through example 1 carefully, and then work through example 3 carefully, and note the differences between the two. This is going to illustrate what the book is getting at in this section. I will say the notation it uses here on 46 and for theorem 6 at the top of 47, the notation is awful. But I want you to understand in this example what's going on, how it differs from example 1. I want you to understand the pictures here at the bottom of 46 and the top of 47. So read the whole blurb. You do need to know this theorem cold. You do need to be able to apply this theorem. The most important takeaway from this section, aside from defining homogeneous and non-homogeneous systems, is this blurb, writing a solution set of a consistent system in parametric vector form. We're going to visit this again and again, and at the point where you know this, you know almost all of the numerical skills that we need to know for this entire term. How to row reduce a matrix properly, and how to solve a system in parametric vector form. I want to point out that step 1, writing a solution set of a consistent system in parametric vector form, is row reduce the augmented matrix to reduced echelon form. I will be checking for this every time. Do not just get to echelon form and then back substitute. I want your matrix in reduced echelon form whenever you are solving a system. And I will penalize you if you don't follow this. Okay? Moving on. We're skipping section 1.6, although it does have some pretty interesting applications. It is worth your time to read if you want to know what some of this stuff is actually being used for. And we're going to pick this up with section 1.7, linear independence. Again, this is a really fundamental concept to the rest of the course. In fact, all of chapter 1 is totally fundamental to the rest of the course. If you haven't been catching this, being really, really conversant with what's going on in Chapter 1 is the key to success in this course. Alright, so at the beginning of 1.7 we make this really odd pair of definitions. Linear independence and linear dependence. These are extremely important, and you do need to understand and know cold these definitions. You should also know what a linear dependence relation is. Example 1 is going to go through determining whether a certain set is linearly independent and finding a linear dependence relation among those variables once we find that they're not linearly independent. Work through this example carefully. At the top of 58, the book discusses linear independence of matrix columns, which is, a certain case where we might want to check linear independence. The blurb here is not a definition. It's one of the how you tells. And this is going to lead us to kind of our general how do you tell. If I want to know whether a set of vectors is linearly independent, shove them into a matrix, see whether the homogeneous system, AX equals 0, has only the trivial solution. And how do we tell? Well, if we want to only have the trivial solution, we need there to be no free variables. Or in other words, every column of the coefficient matrix A must have a pivot. I just said something pretty important, so rewind and think through that a couple of times if you're not following. I may have also just answered an IRAT question. Work through example 2 carefully. Now, starting at the bottom of, 58? Can't see the numbers very clearly here. We're going to talk about linear independence in sets of 1 or 2 vectors, and it's going to get at geometric intuition and kind of how can you tell quickly whether a set of vectors is linearly independent without having to do row reduction. Do read this carefully. The example is important. And I would follow through the discussion through the top of 59. Theorem 7 is going to be extraordinarily important to your understanding of linear independence and linear dependence. You want to get to a point where you have a nuanced understanding of this theorem. The theorem itself is important, the warning is important, and the example is also extremely important. I would work through all these things carefully. The picture here is really good. Okay? Theorems 8 and 9 and the accompanying examples give a couple of special cases where we can quickly tell that a set of vectors is linearly dependent. These are not the only way that vectors can be linearly dependent. I repeat, these two theorems do not give the only ways in which a set of vectors can be linearly dependent. Okay? Again, you need to come to a nuanced understanding of Theorem 7 in order to understand this concept. That's about it for these sections. I would pay special attention to those theorems and all the examples, and you want to come to a place where you really understand what linear independence and linear dependence mean for a set of vectors.